see. Okay. Now it's working. All right. Okay.
Go ahead.
Sorry. Back. Okay. Okay. Yeah. So I'm going to tell you about quantum error correction for gravitational algebras at large N, and this is based on this paper. Now it's not working again. Sorry. Yeah, okay, so maybe I'll just use this. Yeah, so based on this paper and several papers to appear, and this is work with my student, Min Lee. Yeah, so the basic idea is we're trying to unify this recent discussion of gravitational von Neumann algebras and an older discussion of holography and quantum error correction. So let me tell you a little bit about gravitational von Neumann algebras. So if we just step back and think about quantum field theory, in the algebraic approach to quantum field theory, in particular using these Haag-Kastler axioms, you start with a sort of set of regions, causally complete regions, and to each of those regions you assign some algebra. Okay, so some algebra of operators. In particular, it's a bit algebra of operators on as a subalgebra of all possible operators on your Hilbert space. And you roughly should think of these as just functions of smeared local operators in this diamond, and products and sums and so forth. So you generate an algebra. And there's various axioms you add to this. I'm not going to write the axioms down. Many of them are sort of self-explanatory. But basically, they're getting at the local nature of quantum field theory. So basically, the important point is not the algebra itself, really, but really how the algebra sort of sits inside itself, how there's subalgebras, and how they relate to each other when they're space-like separated, and so forth. For example, Haag duality, which arose in Cassini's talk, in particular, if I think about complete theories, then we should have Haag duality. That's an important consistency condition. So based on these ideas, many years ago, people realized that the most efficient way to talk about these algebras is to use von Neumann algebras, which is a special class of algebras. They're just subalgebras of all possible bounded operators on the Hilbert space, and in particular, they're type 3 von Neumann algebras. Okay, so maybe that's scary to some people, but basically you should think about this type classification of von Neumann algebras as telling you about the entanglement structure, possible entanglement structure of states in the theory. In particular, we're talking about entanglement between the algebra A and its commutants, right? So the commutant is everything sort of associated to the space-like region that is the region that's space-like separated to this region. And in particular, in quantum field theory, we sort of have this infinite entanglement near this point here, and it's entanglement on all scales, and that's what gives rise to this type 3. Okay. So it's natural to wonder, of course, what happens in quantum gravity. And this is a very subtle question, obviously, because we're talking about localized regions. We have to worry about different variance. We have, if we really want to do something very powerful, maybe we even have to worry about background independence. But there has been some recent progress in a limit. Okay, in particular, we're maybe thinking about this semi-classical limit. And this was pioneered by these authors here. And roughly speaking, in the G Newton goes to zero limit, we have quantum field theory and some sort of extra diffeomorphism constraints that are coming from the gravitational theory. And if you do that carefully, you can sort of find a classification of possible von Neumann algebras. In that case, essentially, because you're starting with quantum field theory, you start with the fact that you have this type 3 von Neumann algebra. And so, for example, in the ADS black hole, you find a type 3 von Neumann algebra or a type 2 von Neumann algebra, sort of depending on how you treat the fluctuations of the energy in the black hole. The same applies for just the Schwarzschild black hole, and there's also a very interesting discussion in de Sitter space, where you have to add an observer to make sense of the diffeomorphism constraints, and then you find another kind of type 2 von Neumann algebra. Okay, so I've added extra von Neumann algebras to the list that I'm talking about, so I have to tell you what their entanglement structure is, and they're also sort of infinite dimensional, but they have a different kind of infinite dimensional entanglement structure. In particular, type 2 always has some notion of a maximally mixed state, okay, or a renormalized maximally mixed state. And there's sort of, in type 2, 1, it can be normalized. In type 2 infinity, it cannot be normalized. Okay, good. Now, an important point in these papers is that you can sort of understand a basic notion of the emergence of geometry in this language. So in particular, if we just stick to ADS-CFT for now, in the G Newton goes to 0 limit, we have this description in terms of this type 3 or type 2 von Neumann algebra. But if we go to finite n, then we're used to this being dual to some thermophile double state. The thermophile double lives in some tensor product of two Hilbert spaces. And then the algebra of operators associated to the right is just all of the operators acting on this Hilbert space. And in particular, because it's of that form, it's a type 1 von Neumann algebra. And that just means, I again have to tell you the entanglement structure, it means there exists pure states. Right? So in this case, there's just projectors like this, and they're pure states on the right. Okay, so that means that we have to have some transmutation of the algebra. So as n goes to infinity, we go from type 1 to type 3 or type 2. And so, this is some property of the large n limit in ADS-CFT. So let's talk about that sort of more carefully. Okay, so I'm going to have the following set up in mind. I have some sequence of theories labeled by some integer. So for example, if we're thinking about the thermophile double, I should have two copies of some CFT, a left and a right. And then, we have a Hilbert space, which is also a sequence of Hilbert spaces. Okay, and there's a left and right Hilbert space. And then, in order to take the large n limit, I need some structure. I can't just do that for any random theory. In particular, we're used to taking the large n limit with some notion of single trace fields, right? So some single trace algebra. If we're thinking about some matrix-like theory, we have n by n matrices, and we take traces over them, and we construct these single trace fields. In order to take the limit, we still need another ingredient, which is a sequence of states. So that's these guys here. And they live in this sort of finite n Hilbert space. And we also need correlation functions to have some nice property in the limit in that state, right? So we have sequence of states, we have sequence of operators, we can compute correlation functions. As n goes to infinity, we should have something like a Wick, some sort of generalized free field-like structure. Okay, so in particular, let's now take the limiting operator and think of that as some formal object, just some formal operator. It's not really acting on any Hilbert space because I don't really have a Hilbert space at infinite n yet. So I'll just think of this abstractly. But we can think of this abstractly, and we can construct an algebra out of it just by thinking of basically words of these single trace fields. Okay, so that's this. And in particular, on this algebra, I have a state. Okay, and what is that state? Well, it just comes from the limit of this sequence of states, right? So I take these phi's, I identify them with the finite n versions here. I take the expectation value in psi n and take the limit. Okay, so I have a algebra and a state, and so in that setting, you can always construct a GNS Hilbert space, and it's basically constructed as follows. You think of the vectors as just given by these abstract words, and then you quotient by null states given by this inner product, in this inner product. Okay, and then on this Hilbert space, you have some representation of the single trace fields, and you can sort of generate all possible single trace fields in various regions. So for now, we have left and right in the thermophile double, so we'll take all the possible single trace fields on the right, and we'll compute their closure, and that defines an algebra. Okay, and so that algebra is going to be the bulk algebra. Okay, and in particular, under some nice situations, you can prove that that's a type 3 von Neumann algebra, so this is essentially guaranteed by two-point functions, and Elliot gave a nice talk about this in the Gong show. So in this context, I want to ask sort of three basic questions. So the first one is, how do we get back to this type 1 algebra? So we have this type 3, how do we get back to the type 1? Another way of stating that question is, how do we see the microstates? The type 2 algebras that you get, okay, sometimes it's type 2, sometimes it's type 3, but the type 2 are nice because they have entropies that you can define with them. Basically, you define it using the existence of this maximally mixed state. And so you have an entropy for your states, at least up to some overall constant C. Okay? So what is this C? And another maybe way of stating this question is, can we show in what sense the von Neumann entropies at finite n limit to the entropies in the type 2 setting? And the final question, because this is strings, I have to ask, how does string theory fit into this? Okay, so this structure was super general that I just said. It didn't really say anything about larger 't Hooft coupling, for example. And so it seems like we could have stringy type theories here. So what makes the difference between stringy and not stringy type theories? Okay, and so today I'm going to tell you about sort of a construction of a quantum error correcting code that's at least attempting to address those questions. I claim, as you'll see now, it's a very natural extension of what I've already told you. So the question is, really, if we want to think of this as some quantum error correcting code, the natural question becomes, how does the bulk fit into the microscopics? Okay, so what is the microscopics? The only thing it can possibly be is the finite n theory, okay, at fixed n. And what is the code? Well, the natural code is the GNS Hilbert space that we constructed. Okay, so we need a map between that Hilbert space and the finite n Hilbert spaces. So we actually need a sequence of maps. Okay, so we'll have a sequence of maps. That's this Vn. So these are linear operators between these two Hilbert spaces. Of course, this is really weird, right? Because we're in a setting where the code, in sort of quantum error correction, you're used to thinking of the code as being some small thing, and then the physical Hilbert space is much bigger, so you can protect the information. In this case, it's sort of reversed. So H is infinite dimensional, has these type 3 von Neumann algebras, and kappa n is, in principle, finite dimensional. In particular, in this black hole case, I can just truncate to e to the s states. And so, how is this possible? Okay, so we'll see how that arises in a little bit, but let me just go through the construction for now. Okay, so the first thing we need is some way to map from the formal sort of fields that I defined, single trace fields, and the finite n fields. But this is basically just a definition of what we mean by a single trace algebra or sector. Given any representation, any formal field phi, I can give you the following trace of matrices, and the only thing that will change is the n in this formula, right? So, or how big the matrices M are, right? So we have that map, and then to construct Vn, we just construct sort of the linear representation of that map on the Hilbert space. Okay, so for this to work, gamma n needed to be linear. I claim that you can make gamma n linear. It's not necessarily exactly what I wrote here. There's some more technical things there. But you can make it linear. Also, in this way, technically, Vn could be very badly behaved, but it's actually possible to make it well behaved under some extra assumptions about the convergence of correlation functions. So it's maybe a little bit more that we have to add than what we're used to, but it's quite a reasonable sort of set of assumptions. And under these conditions, you can show that Vn dagger Vn, which in a quantum error correcting code is typically just the identity, here it approaches the identity. Okay, so as n goes to infinity in the limiting sense. And it does so in a pointwise way. In particular, what that means is that I have to fix matrix elements, and in fixed matrix elements, it limits to the identity. Okay? And this is the key that allows us to take a map from infinite dimensions to finite. In particular, in infinite dimensions, this pointwise convergence doesn't mean uniform convergence. So that means that if I take the operator norm of the difference between Vn dagger Vn minus the identity, it doesn't need to go to 0. And a good example of this is if Vn dagger Vn is just some sequence of projectors that's growing and gets bigger and just becomes the identity, this norm is always 1, so it never approaches 0. Yet in any fixed element, it will approach the identity as required. Okay. Okay, so yeah, so the other case is uniform convergence. So typically in quantum error correction, as I said, you impose v dagger v as 1. You can also get away with some errors in v dagger v minus 1, but not being 1. But usually when you do that, you would just have some uniform approximation to that, all right? So the new thing we're doing is some pointwise version of quantum error correction, okay? And so we gave this a name. It's called we called it an asymptotically isometric code. But okay, so that leaves open the question, does it really work like usual quantum error correction? And the answer is yes. So you can do all the things that you usually do in quantum error correction. It's just a lot more involved to prove that you can do that. Okay, so the first thing you might want to do is operator reconstruction. Okay, so how does operator reconstruction work? Well, in this example of the thermophile double, we want to have some operator that we reconstruct outside the black hole here as an operator in the microscopic theory. So we actually need a sequence of operators. We need a sequence of reconstruction maps. That's this beta n. It maps from the outside of the black hole to the boundary microscopic theory on the right. And it reconstructs the operator in the sense that when you act on a state in the code subspace, that means act on this Vn, it's the same as if you had acted first with this operator and then acted Vn, but only in the limiting sense and only in the pointwise limiting sense. Okay, so everything, all of my limits are pointwise. Okay, and okay, so that's what I mean by operator reconstruction. And in this context, we proved two main theorems, which basically tell you that you have some notion of quantum error correcting code. And the first one was this information disturbance trade-off, which is some version of no cloning. And informally just says that you're maintaining, the bulk theory is maintaining boundary causality. Okay? All right, and let me not say any more. And the second theorem we proved relates to something called the reconstruction wedge, which is the largest bulk algebra that you can reconstruct on the boundary. So I'll call it E. EL is reconstructed from MNL and so forth. And the theorem that we proved pertains to maximal reconstruction. So what does that mean? Well, you can prove generally, using the first theorem, that the reconstruction on the left has to be contained in the commutant of the reconstruction on the right. But if you saturate this containment, that's actually Hugg duality, then there are various interesting consequences. So this theorem says that the following three are equivalent. That's the first one. The second one is some formula for computing the relative entropies in all states on the code. And that formula works in a convergent sense. So you take the sequence of relative entropies and they converge to the bulk relative entropies. And there's also some statement about modular theory that I won't say. Okay, so these two assumptions that go sort of into the theorems, right? So the theorems are sort of equivalent statements, but the assumptions that go into those theorems are trivial in the black hole case. We might think about a more complicated setting where we have some extended wormhole. And then, it's natural that you can reconstruct in the causal wedge. And in fact, that's part of the structure that I defined. You can use these gamma maps that I talked about to do reconstruction there. And so you get causal wedge reconstruction. And then the question is, can you extend causal wedge reconstruction to the entanglement wedge? And what guarantees you can do that in a maximal way? Okay, so we don't know the exact conditions for that, although by the HRT formula, we believe that in many situations that extension happens. Of course, the HRT formula is sort of derived using the gravitational path integral, and we would sort of want to get away from that. So we want to put in some independent ingredients and see it arise. Okay. The entropy works as follows, as I promised. If we have some maximal reconstruction like this, that satisfies Hugg duality. And for simplicity, I'll take these von Neumann algebras to be type 2-1, so they have a notion of entropy. Then you can show, under some extra assumptions that I'm not telling you, there's a sequence of numbers that diverges, such that the difference in von Neumann entropies in the finite n microscopic theory minus those numbers limits to the type 2 entropy. And some extra things, in particular, this von Neumann entropy is not actually the von Neumann entropy, it's some smooth version of the von Neumann entropy. Okay, Good. So this, in some sense, answers the question of what this sort of unknown shift is in the type 2 entropy. Okay, so another set of things you can do is study vacuum codes. In particular, we can think about now just one copy of the CFT, and we can think about our sequence of states as a sequence of vacuum states. Okay? And a vacuum code is one where I additionally assume that the bulk has a representation of the conformal group, SOD, 2. And in particular, that representation is consistent with the microscopic representation of the conformal group, which always exists. And that's this statement that, in a limiting sense, this is true. Presumably, you would have this exactly true, but to make the statements that I'm making, you can have it approximately true. Okay, good. So in this context, now we want to talk about sort of operator reconstruction in the bulk related to boundary regions that are causal diamonds on the boundary. So here's my boundary cylinder. I have causal diamonds on the boundary. And the question is, what bulk what operator algebras can I reconstruct on the GNS Hilbert space? And we have two naturally defined things. We have this causal wedge and possibly a maximal extension, this entanglement wedge, which is this guy. And in particular, the maximal extension here now pertains to this causal diamond on the boundary and the causal diamond that's space-like separated to that. So that's this dashed line here. Okay, so what can we show? Well, in vacuum codes, we can show that for whenever your boundary causal region is a double cone region, so the intersection of the past and future of 2 points like this, then you can prove, using that structure, that the entanglement wedge equals the causal wedge. That is, the causal wedge is already a maximal reconstruction. And this uses sort of an algebraic version of the Bisignano-Wichmann theorem. It's essentially a symmetry statement. This is not so surprising because there is a conformal symmetry that holds fixed that diamond. And that's key to this theorem. The second thing we can show is more interesting. It's a dynamical thing. So basically, if we have two regions, two double cone regions that are space-like separated, then in certain situations, you can prove that the entanglement wedge of those is also the causal wedge, is also the causal wedge. And in particular, it's if the two diamonds are sufficiently separated in the boundary. Okay, and so there's some condition. D has to be bigger than some DC. And how do we find this DC? Well, it's determined under this theorem by the following condition. So in particular, you want to ask whether the thermal partition function of the theory, we're talking about vacuum codes, but as an auxiliary statement, we're using some property of the thermal partition function. If the sequence of thermal partition functions converges to the bulk thermal partition function, which exists because I assumed that the bulk has the conformal symmetries, and it does so for all temperatures below some critical 1 over d, that sets the condition where you can prove this, right? And so, of course, we expect that to be true below the Hawking-Page transition. Okay, so below the Hawking-Page transition, we can prove this for some correspondence between temperature and distances. What is that correspondence? Well, it turns out it's exactly the following. Given two causal diamonds like this, you can think about their RT surfaces in the bulk, or the minimal surfaces that end on them, and then you can find the minimal geodesic distance between those two. And when that is bigger than 1 over the Hawking-Page temperature, you can prove this theorem that I just gave. In particular, the theorem is that the entanglement wedge of the two boundary regions is equal to the union of the two causal wedges here. That seems like a trivial thing. It's not trivial because it means that as part of it is entanglement wedge is this sort of maximal reconstruction. It means that you can reconstruct this entire region, white region, from the boundary causal diamonds over here. So it's actually a very non-trivial statement, and it relied on a non-trivial dynamical input. Now, one thing about this is that the actual mutual information phase transition, where this fails, is further out than where we can prove that it shouldn't fail. And so there's more work required to reproduce exactly the ADS-CFT prediction. Right? Okay. And I don't have time to go into the proof, but it basically uses the same ideas that go into proving a correspondence between the split property, which I'll mention on the next slide, and thermodynamics. Okay, so now a little bit of string theory. We can imagine a theory in the bulk has some kind of Hagedorn divergence. Okay, so that would happen if the bulk theory was a string theory. In particular, it would happen because I'm imagining taking, say, for example, n equals 4 at finite 't Hooft coupling, taking n to infinity first and then approaching the Hagedorn transition. And in this case, the partition function is just infinite for temperatures above the Hagedorn temperature. And in this situation, for the same reasons or similar reasons to the previous slide, this leads to violations of this, plausibly leads to violations of the split property. So it's the split property in the bulk. So in particular, if I take these two causal wedges here with a dashed line here, they have to be close because I'm imagining lambda is, say, large. But you know, these two algebras would not be in a tensor product relation anymore. So the split property tells you that the union of these two is equivalent, isomorphic to a tensor product, and that's a non-trivial statement. It's not always true. Okay, and in particular, if we have a stringy code, then it can be detected by this condition. So that's one way to, you know, if someone hands you one of these codes, you can say, is it a string theory or not? Okay, that's it. Thank you.
Thank you, Thomas. Questions?
Thanks for the nice talk, Tom. I had a question about this Hawking-Page phase transition. Is this in all dimensions or only in d equals to 2?
No, this is in all dimensions.
So I guess in 2 dimensions, it's not surprising that there's some connection between the mutual information jump and Hawking-Page.
Yeah.
It's much more surprising in higher dimensions. Can you say how you think about that?
Well, let me say for one, unfortunately,
Sorry, you lost your slide.
Sorry, I'm pushing the wrong button.
The pointer's not your friend today.
Okay, yes, good. All right. Yes, so what was I saying? Yeah, so let me just say there should be a tight connection. In this situation, it's not that tight. So in 2 dimensions, you still have this gap between where we can prove it and where it exists. So yeah, I mean, and I think the thing you're thinking about is the connection to the Renyi entropies, which at n equal to 2 is an exact connection. Of course, we're not talking about Renyi entropies here. In some sense, they're not really accessible. So yeah. Now, in higher dimensions, it's just through this split property proof. So basically, the split property uses, to prove the split property, you use properties of the modular operators for the 2 regions. The modular operators are sort of constrained by conformal symmetry, and they turn out, you know, the combination that tells you whether you have the split property or not turns out to be some trace of the partition function. And so that's it, and yeah. And it's the same thing that lets you prove that, you know, you have entanglement wedge reconstruction in the 2 causal, the union of the 2 causal regions. Yeah. So I just told you the words of the proof, but maybe it wasn't very helpful.
Okay, Atish.
Yeah, so this transition from type 3 to type 1,
Yeah.
Is it clear to you that it requires finite n and not finite 't Hooft coupling? I mean, in other words, is the fact that you get type 3 algebra a property of supergravity limit or of the perturbative string theory limit?
Well, from what I've told you, it seems very blind to the 't Hooft coupling. So, yeah, I think it's more a property of large n than a 't Hooft. I think there could be some situations where, maybe depending on exactly what model you're studying, maybe you're not studying a matrix model, a vector model, or something. Then it can be very different. But yeah, in the n equals 4, I think it's pretty blind to the 't Hooft coupling.
Yeah. Yes.
I just wanted to get some intuition for what you're saying here about the stringy limit.
Yeah.
So the algebra you would have said was there would have been emergent type 3 above the Hawking-Page transition in n equals 4. But what happens above the Hagedorn temperature?
No, these algebras are all type 3. It's just really a question of whether you're sort of violating the split or not. Yeah, so everything is type 3 at infinite n, and yeah, it's just another question. In this case, it's either, it's whether you're violating the split in the bulk. You could phrase it as a question about the splitting type 1 factor. There's always a splitting type 1 factor if you have the split property. And yeah, it'll be likely a statement about whether that is type 1 or not in the limit, I think.
Thanks.
Hi, Tom. So in the beginning, maybe you explained this and I just missed it, but in the beginning you talked about how there's type 1, type 2, and type 3. And then did type 2 come back later? Is there a way that you can get type 2 out of this?
Yeah, so it really depends on the setting. So in the thermal case, so in vacuum ADS, we're talking about boundary regions that are type 3. So the bulk will always be, everything will be type 3.
Everything will be type 3.
Now in the thermal state case, depending on your fluctuations of the energy, if you take the strict large N limit, you might end up on a type 3 or a type 2 von Neumann algebra.
Well, so, I mean, one of the issues I had is that my current understanding of the type 2 in ADS CFT is there's not really a well-defined type 2 anywhere in ADS CFT. There's a, it's type 3 if n is infinity, and if n is finite, it's type 1.
Well, I think there is well-defined if you do something where you're not looking at the canonical ensemble and you look at the microcanonical ensemble. So I didn't talk about that distinction. I did say canonical, but yeah, so I had to do something slightly different for that. But if you do a microcanonical window, then yeah, you can prove it's type 2 for sure.
Even at strictly infinite n?
Yeah.
Oh, yeah, that's okay. Yeah, I guess I was thinking more this idea that order by order in perturbation theory, even the canonical one is type 2. That's the thing people say, but I don't know what that...
Yeah, I think that's still true, yeah.
But it would be some perturbative type 2.
Oh, sorry. Yeah. The canonical perturbative, I'm not sure about the status of that. It's not, it's beyond von Neumann algebra, so.
Yeah.
Agreed.
There's a question by Zoom.
So there's a question from Offer Haroni. So which properties that you described hold also in the free limit where the Toff coupling goes to 0?
In the free, yeah, I guess I feel like Offer should be the one answering this question. Sorry. I guess, yes, let's... so really, like the code should be fine at sort of free in the free theory, but yeah, the partition function will be behave quite differently. So I think it will be different, but I don't know exactly how. I have to think more. Yeah. He didn't answer his own question.
Okay, maybe one last Thursday question. Yes.
Yeah, so in the end, I'm wondering to what property, what is the physical meaning of this C extra constant that appears in the Feynman entropy, and to what property of the code is related to?
Yeah, I can't, so I have to admit it's not constructive, it's just there exists a sequence of numbers that gives the answer. So I think many people are trying to get the type 1 in a different way. So including wormholes and things like that, in which case it would be constructive. So that's a difference, yeah. I'm just saying that there exists, right? There exists a sequence of numbers, given the assumptions that went into that. Yeah.
And is it in tension with this assumption of smooth Feynman entropy?
I kind of think that's going to be necessary, whatever you do, just because von Neumann entropy doesn't behave very well under the limits. Especially when your Hilbert spaces are growing. So I think you'll have to smooth no matter what. That's my intuition, at least, yeah.
Okay, let's thank Tom again.